Today, we're very happy to have Anna McLeod. We overlap at ESO, and she's visiting here just for 2 weeks. And so I said, you should come over, visit Gemini, and tell us about what you're working on. So I think Anna will give us a more detailed update. So yeah. Anna.
Yeah, thanks. Yeah, so I was at ESO until last year, where I did my PhD. And I then moved to New Zealand, out of all places. Not directly because of work, but I'm back doing astronomy after a year, sort of forced break. And so yeah, now I'm visiting in Waimea actually. So if there are people from Waimea listening, just go back to your offices, because I'm going to give the same talk next week there. So don't spoil it. Right. So I'm going to talk about a little bit about what I've been working on in the past 2 years, and what I'm going to plan on working on in the next, say, 2-3 years, which is indeed feedback in massive star-forming regions. And the way I analyze these regions is with integral field spectroscopy. So let's see it. Anyway. Right, so just a brief outline of my talk. I'm just going to spend a few words about feedback, what I mean when I say feedback. I'm then going to talk about MUSE and Quemas, which are 2 integral field spectrographs on the VLT. And then I'm going to talk about the ongoing projects I'm working on, and then go a little bit more into specific structures we are analyzing with these data sets, which are ionized pillar-like structures, H2 regions, and then star-forming molecular cloud clumps, and I'm going to try and wrap up. Right, so feedback from massive stars, it's this thing everybody invokes to explain a lot of things, but what is it actually that we mean when we say feedback? So it's a form of deposition of energy and momentum into the surrounding medium by a source, which in this case, we're talking about massive stars. So these are stars that have masses bigger than 8 solar masses. And they do not only regulate star formation in their local environments, but they can also add significantly to the regulation of star formation on entire galactic scales. Right, so there are different feedback mechanisms coming from these massive stars throughout their lifetimes. And in general, this is kind of how we divide them into the different, how we divide these different mechanisms. So we have outflows at the very young stages, when massive stars are still deeply embedded in their forming material, and they expel these bipolar jets. Then we have radiation pressure, which can be direct or just reprocessed, ionization, stellar winds, and at the very later stages, of course, supernovae. Oh yeah, I added a few pictures of all of these. So the main point here is that we see a variety of different types of structures, both on small and large scales, that are driven by these feedback mechanisms. I wish this thing worked. Anyway. Right, so on small scales, we see regions such as, this is the Orion Nebula image I use, where we have a massive cluster sitting somewhere right here. This image is continuum subtracted, so you don't really see the stars, but you see all kind of different structures. There's this bright rim of ionized gas here, then there are outflows, Herbig-Haro objects, and all sorts of stuff going on. We have these curious pillar-like structures that generally we find them in all sorts of different environments and star-forming regions. So these are like pillar-like structures that protrude from the molecular cloud into the H2 region and generally point back towards the feedback driving and ionizing massive stars. So when we say small scales, what we mean is typically parsec scales, so sub or just a few parsecs. And just to put this into perspective, the solar system is about 8,000 parsec from the center of the Milky Way. On large scales, however, we see a kind of different picture in the sense that when people try to explain how galaxies evolve in terms of their stellar content, then they see, for example, that if they seed their simulations with a lot of feedback, then the galaxies tend to form little to no stars at all. However, when they take this feedback stuff out of their simulations, the galaxies form way too many stars and way too quickly. So, of course, we know that the reality is something in between, right? Galaxies have these spiral structures. When they are spiral galaxies, they have sites where stars form and sites where you find cold molecular gas that is just sort of sitting there and eventually will or not form stars. So feedback does something. And we know that from simulations, but what we don't know is the exact prescription of feedback. So if you simulate these things, you really want to know how feedback should be implemented in your simulations. And the bottom line of this is that feedback from massive stars is indeed one of the main uncertainties of star and galaxy formation studies. So if you don't know anything about feedback, you know nothing, they say. Right, so we have this kind of inherent question where we know that we have massive stars and we know that the massive stars do something to their environment. However, and they do so on small and on large scales. However, what is the exact role of feedback? And how does it depend on the properties of the star-forming regions or the host galaxies? And which ones are the dominant mechanisms and at which stage of the lifetime of massive stars and on which scales? So, and at the bottom line, of course, can we quantify feedback? So can we actually, from observations, quantify the effect of these various feedback mechanisms and then go back to the people who do the models and say, hey, so ionization, for example, you need to implement in this way, because we know that from observations. So these are the main questions that are driving what I'm working on. And the way we try to approach this is by doing a twofold comparison. So we take observations of feedback-driven structures and of the feedback driving stars. And we compare these observations to simulations and to each other. So the reason here is strength lies in numbers. So what you really want to do is, rather than observing one specific star-forming region and understand what is happening there, is you want to compare the stellar content and the physical properties of that region to many others in order to disentangle all of the properties feedback depends on. And this is why we use integral field spectroscopy. So I'm always not sure how familiar people are with IFUs, but I already heard there are several people who are quite familiar with this quite neat observing technique. And the reason why it is so cool for these kind of studies is that it offers you the possibility of studying the feedback driven structures and infer physical parameters of these and observe the feedback driving stars at the same time, because for each image in your data cube, you will have, so for each pixel in your data cube, you will have a spectrum that spans the entire observed wavelength range. And that's quite powerful. Yeah, so this is what a data cube looks like when you work at ESO when you use PR images.
So actually, the previous one was for symphony for the first.
Yeah.
So I think for Muse they did something more like, you know, like 3D.
Yeah, exactly. They updated it.
Yeah, that's why it looks good.
Yeah. I know, it looks quite nice, doesn't it? And it also tells you, you know, what the wavelength coverage
Oh
is
yeah,
of this
that one
instrument,
is nice.
and that you can observe, entire galaxies within one snapshot, which is also quite cool. But yeah, the bottom line here is that we can observe the stars and the gas with the same data set. We don't have to go, to do all these messy things you need to do when you try to combine data sets from different telescopes, observatories, instruments, and so on. Right, and specifically I'm working with two IFUs, both are at the VLT. One of them is MUSE and the other one is Quemas. One of them is in the optical and Quemas in the near infrared. And here are just a few, specifications, but they have roughly the same field of view, sort of the same resolving power, and MUSE specifically covers almost the entire visible wavelength range. So when you get data cubes of MUSE, these things are massive, and you can really do so much science with them, because you have everything you need just in one package in 5 gigabytes, to be very precise, for one data cube. So right, a couple of words about the strategy of this project. So the first point is that of observing feedback-driven structures and in further physical parameters. And what I mean when I say feedback-driven structures, I mean H2 regions, these pillar-shaped structures, ionization fronts, but also in smaller scales, protoplanetary disks, so proplids, and star-forming molecular cloud clumps. So if you want to go to the earlier stages of what will eventually maybe be an H2 region. We then observe the feedback-driving stars with, as I mentioned, the same data sets. With MUSE specifically, we can identify and classify all the O and B type stars that are within these regions, and therefore get full senses of the feedback-driving massive stars that are influencing the regions. And then the third step consists in comparing the observations with the simulations and with each other in order to get this dependency on the environment, the evolutionary stage, and the number of massive stars. Right, so we have quite a few observational campaigns completed, analyzed, ongoing, in data reduction, all sorts of different stages. With MUSE, we have observed quite a few pillar-like structures so far. Back in 2015, we had science verification data on the iconic pillars of creation in the Eagle Nebula. We then got another MUSE proposal accepted to observe a variety of pillars in the Carina complex. And we also have another massive data set about the Trumpet 14 star cluster in Carina and the surrounding clouds. We also have 2 observed H2 regions in the Large Magellanic Cloud, and currently in data reduction, a program which observed almost the entire star-forming disk of NGC 300, which is one of the local star-forming galaxies, spiral galaxies. And then we have 3 so far observed 3 star-forming molecular cloud clumps with Quemas. So again, the reasoning here is that you want to go to longer wavelengths in order to start getting a picture of the evolutionary, the dependence on the evolutionary stage. So younger objects, of course, will be observed towards the near and then far infrared. And eventually, if you really want to, you can push it and go to the very long wavelengths. But that is absolutely not my expertise. So now I would like to just point out the 2 colors so that you always know where we are and where we're talking about. So in red, we have small scales, and in blue, what I call large scales. And we combine this with all sorts of archival data sets. So we have, for example, for NGC 300, the exact coverage with ALMA. And then we can, of course, go to data sets such as HST and Herschel and Spitzer, and so on and so forth. And again, so the goal is that to get the properties and the kinematics of these ionized and molecular gas structures as a function of the stellar content of the feedback driving star clusters.
Can I ask a question?
Yeah,
Is there a
please.
reason why you don't do the infrared and optical observation for all of them?
Well, no, not really, in the sense that we have so much optical data right now that we're concentrating on first analyzing and processing that. But we will eventually, of course, want to do a full multi-wavelength study
for all
of them. Yeah. But okay, so the short answer is we don't really have the time right now.
Okay.
Yeah. Right. So ionized pillar-like structures. Tidal is in red because these are small scales. We see them everywhere. We don't only see them everywhere in proper observations. We also see them everywhere in simulations of star-forming molecular clouds that are seeded with some kind of form of feedback. So these pillar-like structures are formed, or at least exposed, so as we think, by feedback. And yeah, as I said, so they also rise naturally in simulations. And again, so this is the Eagle Nebula. By the way, I can't go to a conference on star formation without having this picture or something similar, at least in 3 or 4 talks. They're not talking about these objects specifically, but it's always one of these pretty pictures you show to say things, feedback, or nice pillars. This is another example. This is in the Carina region. This is NGC 3603. So you can see, I mean, we really see these kind of structures all over. This is another region, just to make the point that they're everywhere. Right. So with science verification MUSE data, we covered these iconic pillars of creation. I can't see them anymore, but this is an HST, H-alpha image, and what we did was we proposed to cover the main pillar bodies with 9 MUSE pointings. So this is a mosaic that is about 3 × 3 arc minutes in size. And this is what it looks like. As you can tell, the image is not as neat as what you get from HST. Of course, we don't have, the exact same spatial resolution, but what you have to appreciate is that these are 9 pointings with MUSE. Each pixel in this image has a spectrum across the entire visible wavelength range. And there are about 100,000 spectra per pointing. So, times 9. So it's quite massive.
I have a quick question.
Yeah.
So there's like 4 red sources there. Those are like sulfur 2, I guess, things, right?
So these are stars,
pillars?
yeah.
Are those just cleaned out of the HST image or something?
Yeah, so this
delete
image is
them
not,
for-
this image is not continuum subtracted, so you still see the stars.
Oh, okay.
Yeah.
Okay. I got it.
So by the way, so this is a 3-color image, yeah, so red is sulfur and green is H-alpha and blue is O3. Right, so what we did with these observations was we we computed feedback related parameters, and we had a look at the kinematics of these structures. So we calculated roughly what the electron densities and temperatures are, specifically at the tip of these pillars. So the tip of these pillars are facing directly towards the ionizing massive stars, and so they show these ionization fronts at their tips. And we also computed the photoevaporation rate of the pillars. So what's happening here is that due to the incoming ionizing photons, these pillar-like structures are being literally evaporated. So they're being destroyed by the radiation that's coming in. And as a consequence of that, you have matter streaming away radially from these structures. And then we tried to compare what we found from the observations to simulations of these kind of structures. And here's an example of what we did. So because with MUSE, we had essentially all of the nebular emission lines in the visible wavelength range, we tried to see how these behave at the tip of the pillars. So now you can have a look at these red lines that go down, and these are fake slits positioned on the tip of the pillar. So you have to imagine that you're sort of outside in the H2 region, and then you're walking towards the pillar tip, and then you're going into the pillar material itself, and that's what's happening on this plot. So this is the distance along the profile from the top down, and the intensity of the various emission lines you see. And what you see is this typical trend of ionization fronts, where the species that have the highest ionization potentials peak first, further out. So we have O3, for example, which is always the one that peaks first. And then you have the ones with lower and lower ionization energies that come in a row. And if you compare that to simulations, you find sort of the same behavior. Of course, in this case, we don't really have the resolutions to disentangle between the N2, S2, and H alpha lines. But still, the profile looks about the same, and you see the same behavior. So this is very interesting. Then as things go, you can also, hope for serendipitous discoveries, and this is sort of one of them. And what you see here is this red blob at the tip of the middle pillar, which had not been addressed with all the many previous observations. And what we did was just compute kinematics of these things, and we noticed that at the position of that red blob, we saw a blue shifted, so this is an H alpha velocity map, a blue shifted blob. And then at the tip of the pillar, there is a red shifted blob. And so we went back to past papers and we tried to figure out whether there was actually anything forming at the tip of the pillar. And yes, there is. There is a low mass young star forming at the very tip. And that's that white circle right there. And what we believe we are seeing here is the bipolar outflow from this object. And the reason we're not actually tracing a full-blown jet here is that, first of all, on this side, where the jet is tunneling through the pillar material, it is just now only emerging from the pillar material. So it hasn't fully broken through. While at the tip, the ionizing conditions are extremely harsh. So at that point, the jet is being sort of, lost in the H2 region. Right, so we thought, pillars are nice, let's, observe some more. And we proposed to observe pillars around the massive clusters Trempler 14, 15, and 16 in Carina. Again, with Muse, because Muse is fun. And so, yeah, so this is what the observations look like. They are mosaics of various sizes of these structures. And now, I don't know whether you're familiar, so my supervisor at ESO was Leonardo Testi, and people always, tease me with the fact, and he's from Florence, okay? So they always tease me with the fact that I only observe these to please him, because they kind of look like Florence, but that is not the case. Right, and so, just to show you, we tried to sample pillars around different clusters in order to sample pillars in different conditions. So this is one of them close to Trempler 15. This is very close to Trempler 16, and so on. Right, and we combined these this one data set with what we previously already had for M16, and with an archival Muse data set of a pillar in, it's not very nice, but there was a pillar in NGC 3603. NGC 3603 is one of the most massive star-forming regions in our galaxy. So again, so this was to even, to add to this sampling of pillars in different environments under the influence of different ionizing stars. And the questions we had in the proposal were two. So can we, now that we know we can use Muse to identify outflows of pillars, can we do the same thing as we did in M16 for these observations? And then the main set selling point of the proposal was to compute the mass loss rate due to photoevaporation of these pillars and other quantities such as the electron density and electron temperature, and compare that to the ionizing photon flux coming from the massive clusters in the vicinity of these things. So what we wanted to see was, is there actually a correlation between the mass loss rate or other physical parameters and the ionizing photon flux coming from the massive stars? I'll get to that, but first, outflows. We did, in these pillars, find, again, outflows or jets from young forming stars. This is, for example, one of them. So again, you have a pillar, and then at the tip of the pillar, you have, lots of maser activity and infrared sources. So disentangling which one is the driving source is not always very easy, but yeah. So what you can do is, of course, because you have the spatial and spectral resolution, is to try and understand what's happening in terms of kinematics and properties in these regions. And this is, for example, the sulfur to velocity map. You do see, some blue shifted blobs, which correspond to these, and you can't properly see it, but A and B regions there. This is the H alpha velocity map. And in the H alpha, you can already see, something sort of red shifted there. But it's not until you go back to the data cube and you actually scroll through it around the H alpha line that you can appreciate that there's actually, yes, an outflow. And the reason we see this, and again, I can't properly draw with my mouse, but this should be an emission line, so it should be H alpha, when you have nothing. However, what you can see are emission line wings, or peaks that are H alpha emission line peaks, just red and blue shifted. And so when you scroll through the data cube, you go from here all the way to there, you see exactly that. Oh, hang on. Is this a video? Let's see if it's right. Yeah. Yeah. So this is scrolling through the data cube, and what you see is the blue lobe, so we're here, and the central H alpha, and then the red lobe. And so that's pretty neat. And these things are not seen in H alpha images because the H alpha images do not cover the emission line peaks, red and blue to the line. And this is what a 3-color image of these emission line peaks would look like. So you clearly see the red and blue shifted lobes of this outflow. And then the other thing is the analysis of the photoevaporation rate. And we computed the photoevaporation rate of all of these pillars, and we compare that to the ionizing photon flux they are sort of feeling. And we did indeed find a very nice correlation between the two. And again, what you should appreciate here is that these are not pillars around the same stars. These are pillars around different type of star clusters. And these are not only pillars in one single star-forming region. These are pillars in different star-forming regions in the Milky Way. Right, so just to make things clear, one is the photoevaporation rate, and that clearly correlates with the feedback effect from massive stars. And we then compared this correlation to what you would expect from analytical models, and within a factor, it's quite nice. It actually agrees. So now we have an observational quantification of photoevaporation rate due to the ionizing feedback from massive stars. Right. Moving on to larger scales. So we thought, pillars are nice and the Milky Way is nice, but we really, what we should really do is go and have a look at feedback structures on larger scales. So why not observe entire H2 regions? And of course, doing that in the Milky Way is hard, as you all know, because of extinction in the Milky Way, and because, of course, H2 regions are quite big, you know, on the sky if they're local. So imaging them with a high pressure instrument and telescope such as MUSE and the VLT is not a good idea. It's not going to go past the TAC if you propose for it. So we went to the LMC because we thought, you know, it's the perfect location to look for these things. It's not too far away. It's nearly face on. It has a low metallicity. It has a low dust content, and it has a lot of active star formation. So we proposed for an initial sample of 2 H2 regions. One of them is down here, and the other one is up there. This is N44, which is that I noticed. And this is what these look like. And the reason we chose these, well, you know, so these are 2 mosaics of 8 × 8 MUSE pointings. So these are 64 and 64 MUSE pointings. So they are quite massive, and it amounts about to 30 hours of telescope time. We had to choose 2 because we couldn't go for more for an initial sample. And we chose these 2 because they are inherently different. One of them, N180, is, you know, nice, round. It looks like a typical spherical bubble that is expanding. And the other one has this kind of dark H2 region right here, and then these blobs of more recent star formation around it. They also differ quite a bit in terms of stellar content. And the other interesting fact about N44 is that a supernova remnant is found somewhere in its vicinity. So, you know, they're different, but similar enough to do a nice comparison. So this is work under progress. We have just started analyzing this, but for example, you do see a bit of the mosaic here, but what you can do is kinematics. So this is an H-alpha velocity map, and you can clearly distinguish the ionized matter from, you know, the surrounding, which is quite neat. So you can determine things such as their expansion velocities. What you can also do, and this is very fresh stuff, very recent, I've been working on this just last week, is you can determine quantities such as the radiation pressure from the stars that sit in these regions on the gas. And they do look different. They do look different. So this is the radiation pressure as a function of radius. So you assume that the center of these things is at the center of your image, because that's, you know, how we set up the observations. And then you have a look at how the radiation pressure behaves in radial bins. And they do look different because they are. There's a lot more stuff going on here. You have a lot more ionized emission coming from the center of this region than this one. And you can also do this exercise, of course, not only for the entire image, but you can concentrate, you can cut out, you know, little pieces and do the same analysis on the smaller scales. And again, so we know the stellar content of these 2 regions. We don't know about whether it's a full census of massive stars or not, but now with the MUSE observations, we can actually go and extract all the spectra of the stars sitting in here and have a look at whether our catalogs of O and B type stars are complete. If not, we can add to them, and we can determine what the energetic input from these stars is. Right, again, work in progress.
Can I have a quick?
Yeah, please.
Do you remember what is the exposure time you had for the H-alpha emission map?
Yeah,
the
90 seconds.
90 seconds.
Yeah.
Okay. It's amazing.
And, yeah, so we
and
could
you
have
get this thin filament and stuff.
Yeah, so we could have gone deeper. We didn't because of skylines. That's the, you know, MUSE has
Really nice.
yeah, people are having a hard time subtracting the sky from MUSE cubes. So we thought, you know, let's not do these things because we can. But now we have observations of NGC 300, which is not 50 kiloparsec away. It's 2 megaparsec away, and there, of course, we had to expose for 900 seconds, and we're left over with all of these skylines we're trying to get rid of. But luckily, the main emission lines we're interested in are quite bright, and not so much in the red part of the spectrum where the main skylines are. But yeah, so again, so we thought the LMC is nice, and we're certainly going to want to expand our initial sample of 2 H2 regions to a large program. But in the meantime, let's go and have a look at something even, bigger. So we propose to observe NGC 300, which is a grand design spiral galaxy with MUSE, and this object had been observed during science verification. And these are these yellow pointings. But the observations, although they're quite, they have the same exposure time as what we proposed for, they're not in a mosaic. They targeted, specific science goals, which were planetary nebulae and these kind of things. They're all, misaligned with respect to each other. And so we thought, no, we have this beautiful ALMA data set, which is in blue. We really want to have sort of the same footprint with MUSE, and it needs to be a mosaic. It needs to be continuous. We don't want to have single pointings. And it went through. And so these are 35 MUSE pointings now, so 7 times 5. And we just started reducing the data now. So I don't have much to show here. But again, so here what we want to do is to sample star formation as a function of location within a single galaxy. We have over 150 observed H2 regions in the entire field. And we have this beautiful ALMA data set, which will complement nicely in the sense that we're now actually tracing star formation from the very dense cold stages to the exposed stars and the H2 regions. And this is, so these are 3 pointings, roughly here. And these are the only 3 I've reduced so far. It takes quite a bit of time to do these things. But what you can see clearly is, we have H2 regions here, and we have other things we can also resolve, such as planetary nebula. And then we have curious things, we have no idea what they are, such as this green point here. And that green point source is only visible in H alpha. It has essentially nothing else in emission other than H alpha. And the H alpha is quite broad. And when you search for this object in Vizier catalogs, then you don't really get a specific answer as to what it might be. So if anybody of you works on accreting, late stage stars, just come and talk to me, because you might want to have a look at the spectrum, because I'm not going to work on it. It's one of these serendipitous findings. Maybe somebody will eventually know what it is. Anyway, so this is work in progress. And we're now also collaborating with people back at ESO on dwarf starburst galaxies, because there is about 15 of these observed in the MUSE archive, which is quite nice. You just grab the data and reduce it, and these are typically single pointings. And again, here we really want to understand how the feedback quantities we can derive from these observations depend on stellar content and so on and so forth. Right, just a few words about Quemas, because so far MUSE has been the star of the show. So yeah, if you want to observe younger objects, so not fully evolved H2 regions, you would like to go to the near infrared, and Quemas is perfect for that. It covers, all the main near infrared bands, and we propose to observe 2 star-forming molecular cloud clumps with Quemas in the K band. So in the K band, you have things such as bracket gamma, so you have the ionized gas, and you have H2, so H sub 2, you have the molecular gas, which is quite nice. We observed, I mean, probably won't tell you anything, but BYF73, W33, and W49, and this is what it looks like. Unfortunately, the Quemas data is giving me a bit of a headache because the instrument comes with problems in the illumination on the single IFU units. And that's why you see these weird checkerboard patterns on the images. And we're trying now to understand how we can correct for these and get rid of them, and how, if we can't properly get rid of them, they might influence the analysis. But again, so what we are trying to understand here is, how does the molecular gas and the ionized gas fit into the global picture of star clusters that are forming within these regions? And I'm not going to go into much detail about these three because I won't probably have too much time. But let me just quickly glance at one of these. So this is W49. Again, it's one of the most massive star forming regions in the Milky Way. And there are many things happening here. Mainly, there is a very massive cluster forming right here where we in the near infrared are completely blind. We don't see anything, but you do see traces of massive star formation when you go to very long wavelengths. But with Quemas, what we can do is, so this is bracket gamma intensity map, and this is the velocity of the bracket gamma line. And you can clearly see feedback-driven structures, such as expanding bubbles or kind of outflow things. And again, with the same data set, you can go and get the spectrum of the stars. You can classify the stars. Yeah, but that's also work in progress. So there is a lot, going on. A lot of things that we still need to work on, and we're trying to do this on quite rapid timescales. Let's see if that will actually work. But to wrap up things, so we use integral field spectroscopy because it is ideal to trace star formation feedback. You can cover the feedback-driven structures and the feedback-driven stars with the same unbiased data sets. And the advantage here is, of course, that you have this large scale, spatial, and spectral coverage with these kind of instruments. As I said in the beginning, the strength lies in numbers. So we really need the large observational campaigns in order to get the number of regions we need to do proper comparisons. So first results do show nice correlations between, for example, physical parameters of feedback-driven structures and the feedback-driven stars. So that is encouraging. And we are now working towards an observational quantification of ionizing feedback based on what we have obtained so far. If I had a wish list or a to-do list for the future, then it would of course, include a disentanglement of the feedback properties on the environment. We would like to have a MUSE large program to survey star forming regions in the LMC. 2 are nice, but certainly not enough. And the LMC is the ideal region to do this. Although MUSE is not accepting large programs for the next 2 semesters, maybe next year, because they're commissioning now the adaptive optics and the small field of view. We would like to sample more entire star-forming galaxies, such as NGC 300, really, which would be quite nice. Luckily now, many of these have been observed in the local universe, such as M33 and M81 have all been observed with MUSE, and the data sets are public. You just need to download them and reduce them, which is a bit cumbersome, but you can do it. You would like to trace feedback across evolutionary stages, and so here now I come to your question at the very beginning, because you really want to have the full picture, and you need the multi-wavelength approach for this. Right, and in the end, or maybe while, you would want to do the comparison with the simulations. So what you want to do then is, of course, is you want to fine tune the simulations based on what you got from the observations. And the main point here is that many of the simulations, so none of them include all of the feedback mechanisms. Some of them only include ionization, some of them include ionization of stellar winds, others have supernova, and that's it. So, and they still can't reproduce, the observed star formation rates and star formation efficiencies. And they really depend on this observational quantification of the feedback. And I'm gonna stop right here and thank you all for your attention. And if you have any questions, please